So in this question, we need to solve for K when we are given the reaction equation and the concentrations of the products and the reactants at equilibrium. So the first thing we need to do is make sure to balance the equation. And as you can see in green, I've written the balanced reaction with the proper coefficients. So we have 4NH3 plus 3O2 reacts to produce 2N2 plus 6H2O. So the next thing we're going to do is write out our givens from the question. And as you can see, I've written the equilibrium concentrations of each one, but I've crossed out H2O, and that's because in the equilibrium law equation, you only include gases and aqueous solutions. You cannot include any concentrations of pure liquids or solids. So in the next step, you can see that my equilibrium law equation is my product over reactants. So we have the concentration of N2 and the and it's squared, which represents the number of entities there are. So N2 squared, because there's 2 moles of N2, over NH3 to the power of 4, because there's 4 moles of NH3, times O2 to the power of 3, because there's 3 moles of O2, and I haven't included the H2O because it's a liquid. And then we just sub in our values, and just making sure we're being careful to separate it in your calculator, since it's scientific notation and there is to the powers. So you need to make sure that you separate each value in parentheses, and carefully do it to separate the scientific notation from exponents. And your calculator double check, and you should get this answer, which is K equals 3.59 times 10 to the 24. In this question, we are trying to solve for the equilibrium concentrations when we are given K and this equation. And so the first step that we do is we have to balance the equation, and as you can see, I put the coefficient of 2 in front of the HCl to make the equation balanced. And then the next step is writing our given. So the concentration of our HCl is 0.5 moles per 250 milliliters, which we need to convert the amounts to moles per liters, which will give us 2 moles per liters. So don't forget to do that. And then our K is 3.2 times 10 to the negative 34. And the next step, we have to use an ice table to help determine the equilibrium concentrations. And you just fill it in like that. Next, we have to make the equilibrium law equation, which is the products over the reactants. And as you can see, we have the concentration of H2 times the concentration of Cl2 over the concentration of HCl squared, because we have 2 moles of HCl. And then we can now sub in our values from our ice table, the equilibrium concentrations, into the equation, which gives us K equals x squared over 2.00 minus 2x to the power of 2. And you can see that that's unsolvable because we have x on both the bottom and the top. And the only way we can solve this is either if we make an assumption or we use the quadratic formula. So the first thing I'm going to do is see if any assumptions can be made about x. So I apply the 100 rule to see if x can be assumed to be negligible. So I use the concentration of HCl, the initial concentration, over K, which gives a value that is much greater than 100, which therefore means that x can be assumed to be negligible, which also means that it's less than a 5% error, so this is warranted. And then from there, we know that since x can be assumed to be negligible because it's such a small number, we know that 2.00 minus 2x is approximately 2, which means that the concentration of HCl equilibrium is equal to the initial concentration of HCl minus 2x. And as we said before, 2x is a very small number, so HCl at equilibrium is approximately equal to 2.00 moles per liter. And then to solve for the 2 other concentrations at equilibrium, we solve x. Since we've determined that it's negligible, it's just x squared over 2.00 squared, which approximately equals our K value, 3.2 times 10 to the negative 34. And then once you solve for x, you can now sub in the x value into our equilibrium concentration values. So now we have H2 at equilibrium is equal to X, as well as O2 is equal to X. And since we've already solved for X, it's pretty easy, which means that both our concentrations of H2 and O2 at equilibrium are equal to 3.58 times 10 to the negative 17. So in this question, we are given our K value and the initial concentrations to see if the system's at equilibrium. And so the first thing we need to do is we balance the equation. So as you can see, the green represents the coefficients that I used to balance it. So we have 2Cl2 plus 2H2O reacts to produce 4HCl and O2. So first we write our givens, and as you can see, the H2O has the concentration of H2O is an X because our reaction quotient and as well as our constant law equation don't include pure solids and liquids. So that's why we don't use that concentration. So now we can sub in our values into the reaction quotient equation, which is just the products over the reactants. So we have HCl to the power of 4 because we have 4 moles of HCl times O2 over Cl2 to the power of 2. And like I said, we don't include the H2O because it's a pure liquid. And now we can just sub in our concentrations that we're given, which gives us a Q of 6.48 times 10 to the negative 11. And now we compare our Q with our K. And when we look at our K, we have a value of 2.5 times 10 to the negative 3. So our K is much greater than our Q, which therefore means that the system's not equilibrium, and equilibrium will shift to the right. This question, we use KSP to predict if a precipitate will form when we're given the reactants. And so our reactants are CaCl2 and Na2SO4. So the first thing we're going to do is write the double displacement reaction and balance it. So we know that once we write this out, it will create CaSO4 and 2NaCl. And so the next thing we're going to do is we use a table. So on page 465 in the textbook, table 3, we use a solubility table to predict precipitation. And when we look at the table, we see that the solubility rules indicate that CaSO4, which is a solid, has a low solubility, and NaCl is highly soluble, which means therefore that a precipitate of CaSO4 may form. So now we can write the balanced dissolution equations, and we know that since it's CaSO4 that predicts that a precipitate may form, it's going to be our Ca2 plus ion and our SO4 2 negative ion, like I've written in step 2. And then the next step, we write out the ratio. So we know that since each dissolution reaction has a 1-to-1 mole ratio, the initial concentration of both ions are the same as the given concentration of respective ionic compounds. So therefore, the concentration of Ca2 plus is equal to the concentration of CaCl2 because they have the same mole ratio, as well as SO4 2 negative and Na2SO4. So we have a concentration of Ca2 plus of 4 times 10 to the negative 2 moles per liter, and a concentration of SO4 2 negative of 2.00 times 10 to the negative 3 moles per liter. So now we can solve for Q by subbing in our values, like our concentrations. So that will now, which means that to find Q, it is 4.00 times 10 to the negative 2 times 2.00 times 10 to the negative 3, which gives us a value of Q of 8.00 times 10 to the negative 5, which is our reaction quotient. And this is also called the trial ion product equation. And now, since we were given a KSP of 9.5 times 10 to the negative 6, the value we were given, we can compare Q and KSP. And since Q is much greater than KSP, we know that the equilibrium will shift to the left, and a precipitate of CaSO4 will form. So in this question, we are given the concentration of HCN, which is 6.18 times 10 to the negative 3, and we are trying to find the pH and concentration using the Ka of a weak monoproctic acid. So the first thing we do is we write our givens. And so our equilibrium constant, Kw, is, like I said, a constant, so it's always 1.0 times 10 to the negative 14. And if you look in Appendix B5, Table 1 in the textbook, you find the Ka of HCN, which is 6.2 times 10 to the negative 10. And now we can compare Ka and Kw. Ka is much greater than Kw, and so although HCN and H2O can both produce H plus like ions, Ka of HCN is much greater, so we can assume that all of the H plus ions come from HCN. And so the next thing we're going to do is create an ice table to determine our equilibrium concentrations, and we don't look at the concentration of H2O because it is a liquid. And in the next step, since we've assumed that all the H plus ions are coming from HCN and not H2O, we solve for Ka by subbing in, so by making our equation is the products over the reactants. So we have H plus, the concentration of H plus times the concentration of Cn over the concentration of HCN. And like I said, we don't have the H2O because it is a liquid, a pure liquid. And now we can sub in our values. So we sub in our K and the equilibrium concentration of the ice table. So we have x squared over 6.18 times 10 to the negative 3 minus x. And since that's unsolvable, so we see like we have x on top and bottom, the only way we can solve it if an assumption about x is made, or we use the quadratic formula. So the first thing I'm going to do is use the 100 rule to see if assumptions about x can be made. So I use the initial concentration of HCN over Ka, which gives us a value of 9.97 times 10 to the 6. And this is much greater than 100, which means that there's less than a 5% error. So x can be assumed to be negligible, which therefore means that we can now solve for x, since we know that 6.18 times 10 to the negative 3 minus x is approximately the same as 6.18 times 10 to the negative 3. So we solve for our x, and we get an x of 1.96 times 10 to the negative 6, which means we can now use our ice table to solve for the concentrations of H plus, which gives us 1.96 times 10 to the negative 6. And now we just sub in the values into our pH equation using our H plus concentrations, which gives us a pH of 5.7. This equation we solve for the pH of a salt solution when we are given the concentration of the acid. So in this case we have NH4Cl equals 9.5 times 10 to the negative 2. And so the first thing we're going to do is we have to determine the major entities in the solution. So we know that it will have NH4Cl, H2O, NH4 plus, and Cl negative. But since HCl is a strong acid, it fully dissociates, so it won't react with water. So that's why I've crossed it out right there. And in the next steps, we can write out our equation, which would be NH4 plus H2O goes to create NH3 plus H0 plus. And we can further simplify that by not using the H2O because it's a liquid, and then simplifying using H plus and not H3O plus. So we have NH4 plus goes to create NH3 plus H plus. And now we can write our Ka equation. So we have our product of reactants, which is NH3 times the concentration of NH3 times the concentration of H plus over the concentration of NH4 plus. And now we can look, so in this step we can look up the Kb and determine the equilibrium constant. And so according to table 3 in appendix B5 in the textbook, the Kb for NH3 is 1.8 times 10 to the negative 5. And we know our Kw because the equilibrium constant, which is 1.0 times 10 to the negative 14. So we can solve for Ka if we sub in those values, which gives us a Ka of 5.556 times 10 to the negative 10. And now we use an ice table to determine the initial and equilibrium concentrations. And since Ka is much greater than Kw, we just assume that all H plus ions are produced from NH4+. So now we can sub in our equilibrium constant and equilibrium concentrations into the equilibrium constant equations. And since it's unsolvable, because we have two x's on the being divided by each other, we have to see if any assumptions about x can be made, or we have to use a quadratic formula. So the first thing I do is I apply the 100 rule to determine if any assumptions about x can be made. So we use the initial concentration of NH4 divided by Ka, which gives us a value of 1.7 times 10 to the negative 8, and this is much greater than 100, which means that we can assume that x is negligible, and we can now solve for x, and we are given x approximately equals 7.3 times 10 to the negative 6. And so we can go back to our equilibrium concentration, where we know that the concentration of H plus is equal to x. And now we can sub that value into our pH equation, which gives us a pH of 5.14. So this question is a real-life application question. So hemoglobin is a protein responsible for transporting oxygen in the blood of mammals. The relevant equilibrium reaction is HbH4 aqueous plus 4O2 reacts to produce HbO24 plus 4H+. If the initial concentration of the reactants is 2.00 moles per liter and the equilibrium constant is 3.2 times 10 to the negative 34, what is the concentration of HbO24 in the lungs at equilibrium? So the first thing we need to do is write our givens. So we know that the initial concentration of HbH4 as well as the initial concentration of O2 is 2.00 moles per liter, and the equilibrium constant K is 3.2 times 10 to the negative 34. And now we can use an ice table to determine the equilibrium concentrations and just fill in the table. And next we write the equilibrium constant equation, which is the products over the reactants. And don't forget to include, like I've X'd out, the O2, because in this case the O2 is liquid. And the equilibrium law equation only includes gases and aqueous. No pure solids and pure liquids. So now we can solve in our equilibrium concentration from our ice table into this equation, which gives us 3.2 times 10 to the negative 34 equals x to the power of 5 over 2.00 minus x, which is unsolvable. So we either need to make an assumption about x, or we need to put it in the quadratic formula. So what I do is I use the 100 rule first. So HbH4, the initial concentration over K, gives us a value of 6.25 times 10 to negative 10 to the 33, which is much greater than 100, which means that we can assume, since this means that this is less than 5% error, so we can assume that x is negligible. So therefore 2.00 minus x is approximately equal to 2. So now we can solve for x, which gives us a value of 8.42 times 10 to negative 3. And the last step, we use now our equilibrium concentration from the ice table, because we're trying to find the equilibrium concentration of HbO24. So we know that HbO24 is equal, the concentration of HbO24 at equilibrium is equal to x, which gives us the final equilibrium concentration of equilibrium of HbO24 in the lungs is 8.42 times 10 to negative 3 moles per liter.